talking about heats of reaction, this heats of reaction lab. That's interesting. Yeah, this is going to be a problem because now it's going to just advance it when I try to write on it. See if I can fix this real quick. I'm recording right now. Absolutely. Maybe if I enable editing? I don't know. Yes.
This is Jeff Watson. This John's,
You can't say names on the videos. I'm posting these on YouTube. All right. So, heats of reactions to determine the heat of formation of magnesium oxide. All right. So, I'm going to take you through some pre-lab stuff, and all this pre-lab stuff is going to have to do with zinc and zinc oxide instead of magnesium and magnesium oxide. But it's basically the same
Sarah
thing.
Vogelman, Alex Brownell, John Ernst.
right now.
Whew, dodged a bullet on that one. Huh?
4 names right there.
All right. So here's our reaction for if you take zinc and you put it into hydrochloric acid. Okay. We actually did this last year. I don't know if you remember. It was very close to the beginning of the year when we did the little. Well, it doesn't matter. Anyway, we did this last year. We put zinc into hydrochloric acid. It bubbles a little bit. Doesn't do a whole lot, but it does react. So we've got a problem here. And this problem is really more like a long description of something that happens, and then we're going to ask some questions about it. But we've got 50 milliliters of 1 molar HCl transferred to a polystyrene cup calorimeter. Translation, styrofoam cups. Stacked inside one another make a really good calorimeter because they actually, don't let the heat out, right? So the temperature of the solution is measured to the nearest 0.1 degrees Celsius. Initial temperature is found to be 20 degrees Celsius. That's about room temperature, give or take. And then 0.329 grams of zinc is weighed out and transferred to the solution in the calorimeter. Chemical equation for the reaction. I don't know why it's up here and down there, but there it is twice. The reaction mixture warms to 23.6. So not a huge temperature change, but it is a temperature change. What kind of reaction is this? Exo or endothermic? Temperature goes up. Exothermic, right? It's releasing heat to the thermometer, okay? So calculate the temperature change and enter it in the data table. That hopefully is pretty easy for you. Do you guys have a data table? On your left? I should be following along with this too. Oh, okay, there we go. So where's that question? Oh, okay. So that's even before we get to letter A. You're just supposed to calculate that temperature change and put it in the data table. So the temperature change, I mean, hopefully we can do this math. 20 to 23.6, 3.6 degree temperature change, right? Okay. So letter A here, delta H equals the specific heat of the reaction. Now they're using S for specific heat. In the equation I showed you, it's C times M times delta T, capital C. That's the way I've seen it most of the time. But they're basically showing you the same equation. It just looks a little different. S is the same thing as C. G is the same thing as mass, right? They're just saying mass in grams, and then you've got your delta T. So it's basically the same thing. Because the reaction mixture is mostly water, we can assume that the specific heat is about 4.184 joules per gram degree Celsius, and the density is about 1.00 grams per milliliter, okay? Now the volume of the mixture is 50 mils, so what's the mass of the mixture? Excuse me. And it says write the mass you calculate into the data table. Let's look back over here just to make sure we know what we're doing. So what is the mass of the mixture now? See, here's where it gets a little tricky because we've got the HCl, right? But we did add zinc into it, right? So we actually kind of got into a little bit of a debate about this summer. I'm not entirely sure I'm okay with that because once we add the zinc into the mixture, we have changed the mass of the mixture. The thing is that I guess I'm probably okay with that. What we came to is ultimately it doesn't make a big difference on your final answer anyway. But the reason that they were still thinking that is because really what we want to measure here is the heat change of the system itself. But the zinc is part of that system that's reacting, right? So I think I'm probably more comfortable. This is the way that the teachers of the class this summer wanted to go with it. I think I'm a little more comfortable if you add the mass of the zinc into the mass of the 50 mils of HCl. All right, so we're going to end up with 50.329. Or I guess, really, if we're adding those two to the correct number of sig figs, it would be 50.33. Does that make sense? Because we've got two sig figs right here to the hundredths place. So it would be 50.33 grams of the entire mixture. And I just think I'm a little more comfortable with that. The people that were teaching it this summer were like, oh, it really doesn't matter that much, but this just seems a little more precise to me. So we'll go with that, 50.33. Which means that these other calculations are going to be a little bit off, so I'm going to have to recalculate them. So calculate the heat of reaction and write the value in the data table. All right, well, how are we going to calculate the heat of reaction here? Right, so we're just basically using our formula here, right? So we've got our specific heat, which we decided is 4.184 joules per gram degree Celsius, times our mass, which we just decided was 50 point, did I say 33? Is that right? 33 grams. Times our delta T, which was 3.6, right? Okay, so once we work all that out, it's going to give us 700 and, was it 3.6 exactly? Was that the right number of sig figs for that one? Yeah, I guess it was. That's unfortunate. So really 760 is what we end up with. And I think this was their argument. Let me see. No, see, it does make a difference because they got 750 using their numbers. Using the 50.33 for the mass, you end up getting 760 when you round to the correct number of sig figs. So we'll go with this. 760 joules, right? Okay, so that's the heat of reaction here. Excuse me. All right. Part B, we need to find the molar heat of the reaction. So we've done a couple of problems like this in class for the calorimetry. Molar heat is usually done in kilojoules per mole, right? So first we need to know how many moles of zinc do we actually have, okay? So we had, now here we can use the number that they gave us. It was 3.329 grams of zinc, right? Actually, this one, I can just show it to you. I'm going to cheat a little bit. Okay, so 0.329 grams. Yeah, you know, I don't like exactly. I need to change this so that it shows things the way I like to show them. But again, you do your dimensional analysis. There are 65.4 grams in 1 mole of zinc. And again, that's just kind of following the rule that because we have 3 sig figs here, we need to have at least 3 sig figs when we round our molar mass. Okay, so that's going to end up giving you 0.00503 moles. Okay. So then once we know the number of moles and we know the number of joules that were produced in the reaction, we can calculate kilojoules per mole. And I guess it tells you to put that in your data table as well, the moles of the zinc. Now the heat of reaction, notice they put that, I wasn't careful with my sign. I should have been. That's a negative 750 because, oh sorry, negative 760 because it's giving off heat. This is exothermic, okay? Okay, so now the molar heat of reaction in kilojoules per mole. We have negative 760 negative 0.760 kilojoules. Is it okay if I do that in my head? Just swing the decimal over 3 places. Divided by, what was the number of moles? I forgot already. 0.00503. Okay? And this one I have to actually calculate because it's going to be different than their number. 0.76 divided by 0.00503. So we're going to end up with negative, 3 sig figs for both, negative 151 kilojoules per, no, yeah, that's right, kilojoules per mole. Okay, so it may not seem like a lot of joules were produced, joules of heat were produced in this reaction, but you got to remember we used a very small amount of zinc, so that's kind of why. So they end up with 150, I ended up with 151. Big difference, right? But it actually kind of is a little bit of a difference. Now wait a second. I rounded the wrong number of sig figs, didn't I? Because that should have been 0.76 when I changed it to kilojoules, not 0.760, because it was only 2 sig figs. All right, so they win. It's 150. They win. Ultimately, it does not make a difference on this particular problem. Now, here's the reason I still want to do it that way, because if it was a bigger mass, it would make a difference, right? And so we just have to be a little careful. And I prefer for you guys to be adding your masses together when you're doing a reaction, okay? So, yeah, in this case, it doesn't make a difference ultimately because we're rounding to only 2 sig figs. It's still going to be 150 either way, okay? And that should say kilojoules per mole to the negative, or times moles to the negative 1, or kilojoules per mole, okay? So that's what you'd put in your data table as well. Oh, forgot that we, this was a question. Is the heat of reaction endothermic or exothermic? And so it's increasing in temperature. Heat is being transferred to the surroundings, which means it's exothermic. Okay. And then this is a good question because it helps you to kind of think about your lab. What measurements had to be made to determine this heat of reaction? So what things do we have to measure here? Temperature. Mass of the zinc, right? And then anything else? You need to know the volume of your hydrochloric acid fairly exactly, right? Because that's going to help you figure out the total mass of your solution, okay? Volume of the HCl solution, initial temperature, final temperature. Okay, so we need the temperature change, I think is what you guys said, which is basically those two things. And then the mass of the zinc. You could do it. Yeah, you could, but ultimately, I think on this one, the molarity doesn't matter that much. As long as it completely reacts, you just need it strong enough that you have enough moles of H plus in there that it will completely react with your zinc. Which is kind of nice. Sometimes it's nice when you don't have to be really precise about at least one of your measurements. All right, so number 2 is going to look a lot like number 1, except this time we're doing zinc oxide instead
Aaron
of
Enderley,
zinc.
if you're still in the building, to the main office. Aaron Enderley,
Okay.
to the main office, please. Thank
So
you.
now it's giving you the reaction for zinc oxide plus HCl. A little bit different. I wouldn't necessarily expect you to be able to predict this one right off the bat. Okay, that's why we're giving it to you. But this reaction mixture goes from 21.0 up to 25.4. So kind of similar to the temperature change when you just have zinc. So the temperature change on this one would be 3.6? Again? Wasn't that what it was before? Am I doing my math wrong?
Yeah, where are you getting the numbers?
I don't know. I'm bad at mental math. Oh, I was subtracting this from this and then forgetting about the negative sign somehow. Okay, sorry. Yeah, 4.4. That's what I meant to say. Boy, I wish I could edit that one out. Okay, So 4.4 degrees Celsius on the temperature change, so a little bit more than the 3.6 we did before. Where am I on the sheet? Okay, there we go. So they're telling you about the same thing again. We're still going to use 4.184. We're going to use 1 for the density of water. Okay? And again, the volume of the mixture is 50.00 milliliters. Now what's the mass? Okay, now again, this is where we diverge just a little bit. 0.962 grams, I feel like that is going to be significant. We'll see. We'll work our way through it and see if it matters. Okay? But our mass is going to be, according to them, 50 grams, but according to us, 50.96, right? So 50.96 is what you would want to write on your data table. Okay? All right, calculate the heat of reaction and write in the value in the data table. So same thing again, same basic process here. So we've got our delta H is equal to 4.184 joules per gram degree Celsius times our mass of 50.96. Is that what we said? I'm very bad at remembering numbers too. And then 4.4 degrees Celsius, right? For the temperature change. No, on this one I guess it's just going to be 2, isn't it? Because of the temperature. So 940 here. But it's, again, it's going to be negative 940 because this is exothermic once again, and this is joules. Okay, negative 940 joules. See how different that is than what they calculated. I can't even see it. Did they say negative 920? Well, they didn't say the negative this time. Temperature did increase, didn't it? Let me make sure. Okay. Yeah, they just forgot the negative on that one. Okay, so negative 940 is the number we're going with, even though their answer key says 920. So you'd put 940 in here for the heat of reaction instead. Negative 940. Why does that keep popping up so quickly? All right, so the number of moles of zinc oxide, again, we're just doing the same process over again. So I'm going to kind of zip through this very quickly here. Number of moles of metal, 0.962 grams. You divide that by the molar mass. And then that's going to give you 0.0147 moles. Okay? So that's how many moles of zinc oxide we have. And then, once again, we're going to find the heat of reaction in kilojoules per mole. So this is where we're going to diverge a little bit. It's going to be negative 940. Well, okay, let me be careful again. Well, let's do this. Negative 940 joules equals negative 0.94 kilojoules divided by our number of moles, which we said was 0.0147. Is that right? 0.147 moles. And that's going to give us our number of kilojoules per mole, which is about 64. Again, it's negative 64 kilojoules per mole. See how close that is to their answer on this one. Haha! Negative 64 instead of negative 63. Take that. Big difference. All right, so negative 64 kilojoules per mole is what we're going to have instead of negative 63. Is the heat of reaction endothermic or exothermic? Well, we just talked about that again, right? Once again, it's exothermic because it's increasing in temperature, so heat is being transferred to the surroundings. Okay, so why did we do basically the same thing twice is the question now. And that's what's going to help us, or pre-lab problem number 3 is going to help us answer that question. Oh, measurements again. We got the same measurement question. Is it any different than the last one? No, same thing, okay? Slightly overkill here maybe. But again, the volume of the HCl solution, the initial temperature, the final temperature, and now the mass of the zinc oxide instead of the mass of the zinc. Okay, so here's where we're going to end up doing something a little different. This is the tricky part. Use the, whoops, no, go away. Why? Well, it's on there. Okay, everybody read this on your sheet, and then I'll put up the answer in just a minute. So it says use the heats of reaction for zinc plus 2H plus yields zinc 2 plus plus H2. And, oh, what the heck, where did these reactions come from? What are they doing here? They changed into net ionic equations, right? And so we have to look at both of the equations here. And basically, what's happening, now you can see this one right here with the zinc oxide. That starts as a solid. But the thing that's not really doing anything in this reaction, there's really only one spectator, right? What's the spectator? It's the chloride, right? The chloride's really not doing anything, so we're just kind of getting rid of that. And then the net ionic becomes, for this one, and I'm doing this a little backwards here because this is the one that was up on the screen already. So zinc oxide plus 2H plus yields Zn2 plus plus H2O. Is that balanced? Yep, looks good. And that's what they have written there, right? Except they have it written as a liquid instead of a gas. Just, yeah, I wonder if that was a mistake. Let's see if they wrote liquid earlier in the... No, they've got gas up there the whole time. Oh, okay. So, yeah, that's... I should proofread these things a little bit better before I show them to you, because the actual reaction here, when they write it in the equation, they're saying the reaction that takes place is producing H2O liquid, okay? So this up here, they just put this as a continuation for each different slide, but they accidentally put gas instead of liquid. All right, so this right here should be liquid for the reaction we're doing, which makes more sense, right? This thing is not getting hot enough that we're going to have gas H2O. We're going to have liquid H2O. Okay, so now back to, well, actually, let me go back quickly to the other reaction here. Again, if you take the chloride out of this reaction, if you do your net ionic, you're going to end up with solid zinc plus 2H plus yields zinc 2 plus plus H2, and that's a gas. Right, once again, that's balanced in charge and in number of atoms, so we should be good there. So those are your two reactions. Now, they're also telling you that the heat of formation of water, they found that to be negative 286 kilojoules. Okay? So basically, now we have 3 different equations that we have found the delta H for. And what they're ultimately asking us to find is the heat of formation of zinc oxide. Okay? That's what we're supposed to find here. Let me go. I have to go too far here. Okay. So this is the slide before the one that talks about that actual question. Well, what's the heat of formation reaction for zinc oxide? What would it be? So to make zinc oxide, heat of formation, or I guess what is the formation reaction is what I should ask here for zinc oxide. Right, it would be Zn, and zinc it typically exists as a solid, right? plus O2, because oxygen, that's its elemental form, yields CNO. Well, there's a little problem with that equation. It's not balanced, right? But in order for it to be a heat of formation reaction, I need to only make 1 mole of the product. So how would I balance this one? Put a 1/2 in front of the O2, right? So this is ultimately the equation we're shooting for, all right? So this is kind of what we were doing in class today with Hess's law. They have given us 3 equations. We know the delta H for those 3 equations. And now we have to figure out how to make those equations add up to this equation. Okay? Does that make sense? Kind of the idea here. I feel like I should let you try to do that on your own without showing you the answer. Except those of you who are watching the video, I accidentally flashed it on the screen twice, and so you could go back and see it. But don't do that. Okay? You should get. Why did I even say that? Because now you're going to think about doing it. But okay. So that's basically the pre-lab. Okay. Now again, I think that's really going to help you with the actual lab procedure here. It says, by analogy with the zinc example provided above, develop a procedure that would produce a value for the heat of formation of MgO instead of zinc oxide. Okay? Include steps to ensure personal and environmental safety. Don't mess up the environment with your procedure. Including appropriate laboratory dress and disposal of waste materials. Also construct a data table to receive the measurements. I would have said record the measurements and observations you must plan to make or that you plan to make when you perform the lab. It says at least 2 days before you begin the lab. We're going to say at least 2 minutes before you begin the lab. Okay? Probably it should be at least 2 days before, but I'll be able to look at it and get a pretty good idea quickly of whether you're on the right track or not. Now, let me just point out a couple of things here. The equipment you have, you're going to have a polystyrene cup calorimeter. All that means, what was that?
I don't know. I usually don't know what that was.
Okay, all that means is, sorry, we just had something fall. You're going to have a calorimeter stuck inside of a styrofoam cup stuck inside of another styrofoam cup, okay? And that's going to be your insulation. Weighing boats, you'll have those available to you, or maybe just beakers to weigh the mass of the stuff in. 50 milliliter graduated cylinder, analytical balance, as long as it didn't just break, and a thermometer, okay? So those are the things you'll have available to you. And I think that's about it as far as what we need to talk about here, okay? One thing I will mention. Obviously, when you're developing your procedure, a lot of times these procedures are meant to help you to know what mass to use. Well, that's zinc, right? You're going to be using magnesium, not zinc. So I want you to come up with a way that you can sort of, by analogy, figure out approximately how much magnesium maybe you should be using, okay? I'm not going to tell you exactly how to do that, but I think you can probably figure it out. Okay? All right, so I think that's pretty much it for the pre-lab. And we'll see you guys on Monday with your hopefully really good procedures so we can get started right away.
Yeah.